Alright, so now that we have learned how to divide vectors into components, into its two individual pieces, an x piece and a y piece, let's use that to actually add vectors together mathematically. A couple of reminders. Pythagorean Theorem, right, is a squared plus b squared equals c squared. Let me translate that into vectors here. So it would be your x component squared, and I'm actually going to use x total, and you'll see why here later. Y total, so all your y components added together, squared would equal the resultant, or the final vector squared. Inverse tangent. Remember, the angle is equal to tan inverse. Now, that's opposite over adjacent, so I'm going to use the y's divided by the x's, x total. And you'll see what I mean by x and y total here very soon. Now, steps for adding vectors by components. Number one is sketch out what you believe is going to happen. So over here on the left-hand side, I have two vectors that I want to add together. So let me sketch that out. This is a tail to tail, so I need to copy paste, right? So I got one vector like this, another vector like that, and I would expect the resultant vector to go somewhere in there, R here. The reason I want you to sketch is that'll give you an idea of what to expect. I'm thinking this vector is going to be somewhere in the 40, 50 degree range, obviously between 24 and 79 here. I'm also expecting it to be longer, a decent bit longer than 1.1, 1.2. Now I'm going to go back and erase what I just did because I'm going to need this picture, but for you, you're going to need to keep whatever you sketch because that's what you're going to compare your final thing against. Now, step two, break all vectors into components. So let me talk about the idea behind this. Here's the thought process. If we break everybody into its individual components, right, so there's those two components, and then here's the components of the blue. If we break everybody into their individual components, then I can set up one big tail to tip triangle, adding all the x's, adding all the y's. So here's what I mean by that. Alright, so let me redraw an xy axis here. XY axis, alright, and I need to make that a little bit bigger here. Now, I'm going to take each of these individual components. So I have a blue X component. It's about like that, right? It's kind of small. And then an X red component that started from over here and ran all the way to the end over there. So I'm going to position it to kind of go on top of the blue. All right, so I'm putting them tail to tip, and I think I said tail to tail earlier, but tail to tip is what we're doing. Now I'm going to come back and I'm going to grab the blue Y component right here. And then I'm going to position it, it's pretty tall, once again, tail to tip, right? And then I take the red Y component and I put it, once again, tail to tip up here. It was pretty short, and I'll get my resultant vector. Let's change the color on this. Running from the tail of the first, and let's actually get that at the right angle here, to the tip of the second. R. Okay, so remember vectors, this is what it's looking like pictorially. Remember vectors, I can move around any way I want as long as they're going the exact same direction, right? Same angle and same magnitude. So here I have rearranged all the vector components, right, to where they're tail to tip, same angle, same magnitude, right, just moving them around and where they're located, where I get all nice tail to tips, which makes it very easy to get my resultant vector going from the tails of the first to the tail of the first to the tip of the last. So now what does that look like in terms of math? Well, let me once again clear some space here to where I can actually show my work since I run out of space on this slide. Alright, so the math behind this. Step 1, sketch. Step 2, break all vectors into components. So I'm going to start out by breaking the 1.1 or 1.2 at 79 degrees into the x component. So I'm going to have this be my x row here and this be my y row. Right there. So the x row for the 1.2 vector, and then the 1.1 vector, and all this is going to make a little bit more sense as I go along. X component, remember, always uses cosine. So 1.2 cosine 79 degrees. Remember, X component, it's always vector cosine the angle. Remember that from the other day. The Y component is 1.2 sine 79 degrees. Okay, so there's the first vector broken into components. Now the X component of the other vector, 1.1 cosine 24 degrees. And the Y component, 1.1 sine 24 degrees. Alright, so now I have everybody broken into components. So it says add all my X components, right? And then I'm going to add all my Y components. So all I have to do now, and this is why I set it up in a nice little table like this, is add these two, right? So my X total is going to come out to be 1.23 with a bunch of other decimals. And my Y component comes out to be 1.625 or 1.63. I'd recommend keeping as many decimals as you can here, but for just the sake of me writing down, I'm going to only keep a few. Alright, that's great. After I add all the X's and add all the Y's, now I'm going to Pythagorean Theorem. That should make sense to you here, because remember, I rearranged all of the pieces in the triangle. Rewind the video if you need to. So I rearranged all the pieces to make one big triangle. I did an X total, I did a Y total, right? So I added up the X's, added up the Y's. Let me see if I can sketch this out again for what I had. So I had a triangle that looked like this here. The two X pieces added together to give me X total, right? And then the two Y pieces added together to give me a Y total. Yeah, so I added these two pieces together and then these two pieces together to get my Y total. So here these two added X total, these two added Y total. And then, so now I know XT and YT mathematically, here they are, right? So if I know two sides of the triangle, right, I can find the resultant, R, the hypotenuse of this triangle here. So I'm going to use Pythagorean Theorem to do this. So now R squared equals my X total squared plus my Y total squared. Remember, we saw that from over here. So R squared equals 1.23 squared. Let's get the pencil going here. Good. 1.23 squared plus 1.63. 3 squared, so you plug all that in the right hand side into your calculator, take the square root of both sides, and you come out with R equaling 2.04 approximately. Now we're not done yet because we have to figure out what the angle is, right? And so we're going to use inverse tangent for that. So theta is going to equal tan inverse of my Y total, which is 1.63, divided by my X total, 1.23. Plug into calculator and you get 52.96 degrees with significant figures. Theta comes out to be 53 degrees, and I actually need to come back here and look into changing this guy, right? Because here this is incorrect. This can't be 2.04. I only have two sig figs. This just has to be 2.0, so let's get rid of that 4. So 2.0 at 56 degrees would be my final answer. 2.0, and I need to give a unit, meters per second. Alright, so let me work another problem through from the beginning here. Step 1 is to sketch. So 2.4 at 85 degrees is going to be somewhere in here, 2.4 meters per second, and 4.7 meters per second at 132 degrees is going to be something like this, right? And so I'm expecting my resultant here, if I do the, it's a telltale, I'm expecting it to go somewhere like this, and it needs to be much bigger than, not much bigger, but it has to be bigger than 4.7, and should be somewhere quadrant 1, quadrant 2, I'm not exactly sure. If I had to guess, I'm going to venture quadrant 2. I didn't actually do the parallelogram like I should have there just due to space constraints. Now let's actually work the math, which is the part that's new, and so that's what I'm focusing on. All right, so the 2.4 at 85 degrees, and I'm adding that to 4.7 at 132 degrees. All right, so x's and y's, right? Break each into their components. So 2.4 cosine 85 gives me its x component, right? And its y component will be 2.4y. You always use sine. And then over here, for this one, x component 4.7 cosine 132, and y component 4.7 sine 132. And then I add the x's and add the y's, right? In the steps, you sketch it out to get an idea that we have something to compare against. Then you're going to break everybody into components. That's what I'm doing here. Remember, cosines for x, sines for y, and then add the x's, add the y's to come out with whatever your x total is and your y total. X total equals y total equals. So you plug all that into your calculator and you come out with your x total to be negative 2.94 and your y total to be positive 5.88. Now, this negative here might seem a little confusing to you, but think about something. Let's come back and let's draw a nice big xy axis. Quadrant 1, and let's actually give positives and negatives, right, for where everything in. Quadrant 1 is positive x and positive y, right? Positive x, positive y. Quadrant 2 would be a a negative x and a positive y. Quadrant 3, both are negative. Quadrant 4, you have positive x, negative y. So all this negative x component, the actual component of the resultant vector is negative here, and the y component is positive. What this tells me is I am expecting to find this answer in quadrant 2, okay, because negative x's, positive y's exist in quadrant 2, and whenever I added and got the resultant components, right, the x total and the y total, I'm coming out with negative x, positive y. All right, so now I need to actually find the resultant. R here squared using Pythagorean Theorem is going to equal negative 2.94 squared. Notice I put the parentheses around the negative 2.94 in the square. Be careful with that, right? Make sure your calculator square of a negative comes out to be a positive, right? Otherwise you're going to end up with square root of a negative number, possibly not in this problem, but it would mess everything up. So you're going to plug everything into your calculator, take the square root of both sides. You come out with 6.6 with sig figs, and that's meters per second. Now I need to figure out what my angle is. The way I do that is with inverse tangent, right? Because I have the opposite and the adjacent sides. So tan theta equals opposite over adjacent. So inverse tan, right, is going to be the opposite, which are my y's. 5.88 divided by my x's, negative 2.94. Plug into the calculator. Come out with negative 63.4 degrees. Now pause for a second. This angle here shouldn't make any sense to you. Negative 63.4 degrees is somewhere down here, right? Negative 63 degrees. And I'm expecting this to be somewhere up in this area, right? I'm expecting my resultant to be somewhere in quadrant 2 from all of this. So this couldn't be right. Well, your calculator doesn't know whenever you plug in a negative here, it doesn't know if you're choosing quadrant 2 or quadrant 4. It just chooses quadrant 4 for you. Let me try to explain why. You have a negative x component and a positive y component, but mathematically, a positive divided by a negative gives you a negative number. Likewise, if this was a negative y and a positive x, that would make it quadrant 4 over here. There's no way for the calculator to know the difference mathematically. So the calculator always chooses your angles to be in either quadrant 1 or quadrant 4, and you need to use a little bit of common sense. You need to use your brain, the brain that the calculator doesn't have, right, to be able to tell, hey, this is supposed to be in quadrant 2. All you have to do is add 180 degrees, right, because it's the exact same angle, just 180 degrees. It's in the opposite quadrant. Now that gives you a theta of 116.5, keeping to, it looks like my two sig figs here, I'll have to go with 120 degrees, which that now makes sense, right? The answer here of 6.6 meters per second at 120 degrees, and let me actually write that all together. That would be a good thing to do here. 6.6 meters per second at 120 degrees is my final answer. It's larger, right, than my largest vector, and it's in between 120 degrees. It's in between these two angles over here. And it should make sense that this one, that the angle is going to be closer to the 132 degrees because this is the larger of the two angles. It's going to pull it a little bit more. All right, let me show you one last problem. I'm not actually going to work this one for you. I just want to give you a word of warning. I have this problem set up 24 meters per second squared, 24 meters per second squared, so the components or the actual vectors coming together are exactly the same here, and they're both at 45 and negative 45 degrees, so these angles are identical. Now, common sense kind of tells you, hey, the resultant vector is going to be right here on the 0 degree line going like this, R, right? Whenever you add them together, your x total will come out to be some large number, right? But your y total is going to come out to be 0. Now, you need to look at this, and without even having to plug into the inverse tan, you're going to realize, hey, this has to be 0 degrees, because at what spot can you have, and this x total would be some positive large number, at what spot can you have no y component? That means it's either this angle, 0, or 180, right, to have a y total of 0, with a positive x. Well, that means the angle has to be 0. Another word of warning on other problems. If it comes out where, if it sets up where you have vectors like this, and the resultant vector is going to come out on the 90 degree mark, you're going to have an x total of 0 in this problem, which isn't the one that's happening right now, and a y total of some positive number. Right? And whenever you plug that into inverse tan, you're going to have this whole can't divide by 0 problem. So you need to go back and look at your components. What angle gives you a no x, that means it's either straight up, 90, or straight down, right? And has a positive y component. That must mean that it's 90 degrees. So a little word of warning on the problems that you're about to do.